Now, developing further the priority queue problem that we have been talking of, let's say we have done the initial heapify for the data that we have. So we have a heap available to us, as we discussed in the last video, which has all the priorities in, let's say, a min heap. Now, a new patient comes in with a priority score of 6. Now, obviously, we have to treat this patient in the right moment. If this patient happens to be the most highest priority at this point of time, well, then this person needs to be treated immediately. So, which means that we have to find the right position for this person. Remember, the goal was that the whoever is the highest priority at a given point of time must be given treatment. So no matter what method we were using, we will recognize this event, but our action from that point on will depend on the method that we have been using. Let's say we have been very lazy, we left the list unsorted. So what we will do is to basically just append this guy to the end. Very simple operation, but then the problem comes when we have to find the minimum. It's an order of n solution. We spoke about this. When it comes to sorted list, so let's say we've done a lot of work, sorted this list, we would apply insertion sort to find where this item needs to be inserted there. Again, this is an order of n operation, although next time when we want to find the minimum, it's order of 1. We spoke about this also, right? But then what happens in a heap case? Remember, we have converted this data already into a heap. Basically, you realize that when a new person comes in, we can put that person into the heap and again restore the heap structure in an order of log of n operations. This is really, really, really beautiful. Let's see this with an example so that we can understand this. Let's say this is my heap presently, right? So essentially a new guy comes in. So remember, this was my heap to start with. Suddenly I have this new patient coming in with the priority score of 6. So all I do is that I add this person to the list. I append this to the list here, which means that this node here, index 5, ends up having one more child, because remember, I'm going to maintain my complete tree property. I'll end up in a different tree, which is not a heap. In fact, I'll end up in a tree like this. So basically all I've done is to add my next item, append it to this to list. Now this is not a heap. However, just like we have seen before, think about it. If I could interchange these two, I will again end up in a heap. And what does it mean? If I were to go and let's say put this item in, let's say, index 5, put this in index 12, I have again got a heap. So I do that. However, when I do that, I realize that, look, there is a violation happening here. Worry not, because all I need to do now is to just make sure that I fix the heap property at this node. That will require me to interchange 6 and 8. So I do one more transformation. Basically, I take 6 to the place of 8, 8 back to the place of 6, just one swap. And bingo, my heap is restored once again. So think about it. I went from being in this situation, this node here went up through the levels and it reached the right place so that the heap structure is maintained. And you can very well imagine that if, let's say, this priority was 1, in fact, I would have made one more switch here and brought it up to the top. So when I'm doing heap operations, notice whichever node is impacted, it's only that node that I have to test, because none of this part of the tree, for example, is being impacted by the addition of this node here. So think about it. Basically, very, very, very few comparisons are required. In fact, all I need to do at most is to jump up, let's say, to the top, and we have seen this before. The number of levels is in fact logarithmic function of the length of the list. Very visible from the, let's say, perfect trees. If you have, let's say, 15 items on the list, well, that's 4 levels, because 2 to the power 4 minus 1 is 16. Sorry, 2 to the power 4 minus 1 is 15. If we have 31 items in the list, that's 5 levels. So which means that if there's a heap with 31 items, I'm not going to require more than 5 comparisons to bring this heap structure back again. This is phenomenal. Basically, I have a heap, let's say, of 1023 items. In at most 10 steps, I can again restore back the heap property, because like I said, the maximum number of steps that the leaf item has to move is log of n. So that's why I said that a new item comes in, restoring a heap back is a matter of log of n compared to, let's say, the sorted case. And when it comes to Python implementation, well, in the heap queue module, there is a function called heap push. So notice here, I have a list here. The list of priorities that we are looking at. I go and heapify this first. Remember, this happens in place, which means P is now heapified. I am telling heap queue to push into this a 6. In fact, it does all of those items. So all it does is to first put this in the end, and then And then through, let's say, maintaining the heap property, it brings 6 to its right place, and in fact 6 ends up here. You notice once I look at P again, 6 has been brought here. So once again this is a heap, and 6 has been brought to its correct position. Just before wrapping up, I just want to highlight a term that you might see in the literature. You notice how in this case the value 6 in fact seems to sift upwards, or say percolate upwards. So that's what this is called, percolate up or sift up. You notice it's literally like, climbing up the ranks to reach its right place. And this is what happens when we do a heap push. Basically the item gets added in the end, but then it percolates upwards. And like I said, significantly, it's only this path that is being traversed, nothing happening on any other path. And that's why this operation remains very, very efficient, right? So very beautiful. Think about it. Happy to discuss. Also, the heap push module, heap push function does it for us in a very smart way. But of course, it helps to understand what exactly happened. And that's what I try to do. I hope you found this interesting. Do look at our website www.ybyte.in, because we always learn programming in a fun manner, getting into details without confusing you in the jargon. Take care. Thank you so much. Bye bye.